So yesterday we were talking about this concept of radiation and radioactivity and radioactive decay, but it's really kind of hard to understand that. So once again, we're going to use a metaphor. Let's talk about Emmy. Emmy is probably one of the most stable people I know. I mean, look at Emmy. It's just, you make fun of Emmy, Emmy smiles at you. You compliment Emmy, Emmy will smile at you. I mean, probably she's one of these people when there's a tornado coming through and she comes, oh well, you know, at least it's going to sweep away all these leaves that are just sitting all over the place. She's a very stable person. Probably when you come back and see her at your 10-year reunion, you'll find that Emmy is still Emmy. Okay? Now, let's contrast that with serenity. Serenity, Emmy, by the way, is a non-radioactive element. That means that if she was non-radioactive potassium a million years from today, she will still be the same atom. Still the same atom. 2 million years, still potassium. Still potassium. She is stable. Now, serenity. Okay? I don't know Serenity that well, but she just seems like the kind of person that will play along here and act like she's unstable, even if she is not. I don't know. Okay, so we're going to make believe that Serenity is an unstable atom. That means Serenity, for the first 16 of her years of her life, she's been Serenity, and she's grown used to being Serenity. Okay? But because she's a radioactive atom, here's Serenity. Do you have a boyfriend?
Yeah.
What's his name?
Nate.
So Nate and Serenity are out on a date, and they're holding hands, and it's so sweet, and they're just walking down a nice romantic path. Then all of a sudden, Serenity stops, and she gets this really weird look on her face.
She started to transform.
And then all of a sudden, there's a pop. Nate gets hit with something on his face, and he gets it, and it's like this red, bloody, slimy thing. And he goes, gross, where did that come from? And then she looks over, and there's a dude standing right where Serenity was.
Turned into a dude.
He's homo.
Hush! It's my story. I get to tell it. So Nate looks over and goes, Serenity? And where Serenity was, the dude goes, Tom.
Hardcore.
And Nate goes, but Serenity was right here. Serenity Scully Jeffers. Tom Scully Jeffers. So you're Tom now? Yes. What happened to Serenity? He kind of looks at him weird. Don't know. But you're Tom now. Tom.
Okay, man.
And Nate, at this point, decides that perhaps this relationship has taken a very strange turn and decides to end it.
Aww.
Sorry.
That's the right.
It was a little
Okay.
spicy. I liked it.
Okay, Serenity has undergone radioactive decay. With most radioactive decays, radiation is given off. In this case, the radiation was a blinding light that accompanied the pop. And the little piece of flesh that came off of Serenity,
Gross.
which we call radioactive particles. We'll have names for these things called alpha and beta and positron and neutrinos and stuff like that. So these are every example of radioactive decay corresponds with a complete change in identity. I mean, we'll have to come up with a brand new Social Security number. Serenity is gone, never to come back again. It is now Tom Jeffers Scully. Scully Jeffers? Scully Jeffers. Tom Jeffers. Okay? and new social. I mean, it's a brand different personality, different gender, and Nate just couldn't handle it. But Emily could. Emily, I mean, Tom comes the next day to school. Emily's going, "Oh my goodness, who are you?" I'm going, "Well, folks, I have an announcement. I heard from Serenity's mom that Serenity is no longer Serenity, it is Tom." Did he have a gender reassignment? No, it's a completely different person that just happens to occupy the same time and space as Serenity did. Okay, so, but Emily over here is going, "Ooh la la, me likes Tom." And so you guys start flirting, and pretty soon they're dating. This continues on through February, March, April, May, and then sometime in May they're going out for a walk.
You got past like Monday?
Yeah, they got past, they went to the prom together. It was great.
Oh my God.
Tom and Emily just sitting on a tree, KISSING and all that stuff. Okay, so on a beautiful spring day, they're walking down the park, and all of a sudden Tom stops and gets this blank look on his face. And then he looks kind of constipated. Then all of a sudden there's a bright light, a pop, and Emily gets hit with a slimy piece of flesh. And she looks, and there is this black-haired, green-eyed, really pretty little girl. Not little, but I mean just a girl. And she goes, "Tom?" And where Tom used to be standing, this girl says, "Monica."
Monica.
But Tom was there. "Monica. What's your last name?" "Jeffords." Emily goes, "It's happened again." So now you got a decision, Emily. I mean, you can continue, you can try to go with the flow and continue on with the relationship, or you can put an end to this. So what's it going to be?
Sure, go with the flow.
Go with the flow. So now it's Monica and Emily. Okay?
Do I get
And
dude
this,
or-
what?
Does it change to another dude or no?
We don't know yet. So they date through the summer into the fall of their senior year. Senior year?
Oh.
What year are you?
I'm a sophomore.
Oh, okay. Junior year into the spring of the junior year, into the fall of the senior year, they're still dating.
Wow.
Into the spring of
my
the
God.
senior year,
What's wrong?
into college, they're beginning to talk about marriage.
Wow.
And then, well, I mean, you'll have to go to a different state, of course. But you can talk all you want. Ain't happening here in Tennessee. Okay? Okay. I don't think it'll happen in Alabama either. So, then once again, on a cool, crisp fall day, you guys are walking together, hand in hand. They walk a lot. And she stops,
That's a healthy relationship.
gets that constipated look on her face. There's a pop, there's a flash of light,
And
there's a
flesh.
piece of flesh, and there is Marianne.
Why?
That's it. You can't take it anymore, Emily. This is a lifetime of waiting at any moment for your boyfriend or girlfriend to become somebody new is too much for you. It has weirded you out. You thought it was over. It's weirded you out, and you ended it. So Marianne, you continue on as Marianne for 35 years. You're married. You have kids.
She aged.
And then,
Holy crap.
yes, after 25 years of marriage, you're
John
celebrating. You change into Pete. By this time, it's been 25 years. Your husband's used to you. You've heard about these he's heard about these strange transformation. Pete loves football. Marianne didn't love football. So I go, oh, what the heck? So they stay married for the rest, for another 50 years. What does this have to do with anything? Because that is the life of a radioactive atom. At any moment, it can undergo decay, releasing radiation, and become something that is radically different. That's right. So the moral of this story is that if you're going to marry somebody, you don't marry an unstable nuclei. You marry a stable one that's not radioactive, right?
Exactly.
Excellent.
Can be stable.
Yes. Who is Sarin? Oh, it's already happened. Sarin, Jeffers Scully.
No.
Sarin.
Dumb.
All right. So, when that light is emitted, let's talk a little bit about that light. Okay, that's question number 5. Let's talk a little bit about the characteristics of that light that's emitted every time serenity becomes somebody new. First of all, it's a form of energy. Form of energy. Oh, we got through this yesterday? Form of energy. All right. So, the higher the frequency, the higher the energy, the more dangerous. We got through all of that.
Yeah.
Excellent. Okay, so here are all the different types of light that can be emitted if serenity undergoes decay.
How did that get there?
Okay, not only it's not the only way that we can get light. Every time you see light, it does not necessarily come from radioactive decay. It can also be as simple as an electron receiving energy and getting all excited and then giving off its energy back out. Okay? When we see this light coming from this fluorescent light fixture, that's the light that's coming from there. It's coming from excited electrons. So either excited electrons will produce light or radioactive decay will produce light. We can only see a tiny little sliver of all the different types of light. Okay? It's called visible light. Our eyes are only attuned to those frequencies.
Well,
Frequency is how many waves pass a given moment at a given point. Think of frequency like this. You go up to the shore of Myrtle Beach on a windy day. You take your watch, set it for 1 minute. How many waves are going to pass your feet?
20,000.
Okay, on a windy day in Myrtle Beach, a lot. That means the frequency is high, right? Wavelength is the distance between the waves. So if they're crashing one after another, what's the distance between the waves? Short, right? One wave, here's another, here's another, here's another. So when the wavelength is very short, that means you've got a lot of waves passing you at a given time. Okay? That's Myrtle Beach. This is Myrtle Beach. You could also have gone to Panama City Beach.
Yeah.
That's from visible all the way to radio. Panama City. All right, let's take our chronometer. Go to the shore. Chronometer, watch. Stopwatch. Let's click so that we got a 1 minute count. Here comes a wave. There it is. It's coming. It's coming. It's almost there. It's where Riker is. Here it is. It's where Matamoros. Oh, how refreshing. It just passed my feet. Okay. Let's see. Oh, there's another wave over there by Central Baptist Church. It's coming now. It's coming. Okay, tell me about the distance between waves in Panama City.
20.
Okay, so the distance, so these waves have a huge distance between the waves. So how many waves can pass in a given moment? A few. So the frequency is low. Which beach is more dangerous, Myrtle or Panama City? Myrtle. I mean, whenever we'd go with Myrtle with the kids, one of us would always be sitting counting heads. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. Missing one. Missing one. Oh, it just popped up. 4. Okay? Why? Because you're afraid you're going to lose one. And if you lose one, then there's all sorts of paperwork you have to do and fill out police reports, and then there's funeral, and then your parents freak out. And it's just you have to keep up with the number of kids you have. Yeah.
What?
Let's not go there. He probably has some weird story to tell us. Panama City, I would go, hey, guys, just let us know if somebody gets hurt. And we would both fall asleep. Why? Because they're not going to drown in Panama City water. I mean, it's like it comes to your knees. And they didn't like Panama City because they like to go body surfing, boogie board surfing. So usually the biggest problem with Panama City is, I want to go to the pool. I want to go to the pool. The pool is fun. The ocean's boring. Oh, too bad. Just go over there. And when we wake up, we'll go to the pool. So, safe, tranquil. Those are the kinds of lights that are not going to hurt us. Okay? So anything on this side is dangerous. Anything on this side is relatively safe.
You made a butterfly.
I did. It's really little specks there. Okay. All right. But all of it is light. We can only see a tiny little bit. What device allows us to see microwaves?
Eyeballs.
No, we can't see microwaves with our eyeballs.
Like the microwave in your kitchen.
They can create microwave light, but they can't see it. How about your cell phones?
Yes.
Your cell phones receive and emit light in the microwave range. It's close to the radio, so it's on this side over here. But some of it is microwave, some of it is radio, some of the frequencies. Okay? What about infrared? How can we see infrared? Night vision goggles. There are also goggles that allow us to see in the ultraviolet. What can we use to allow us to see radio or TV waves? Light. Radios and TV. Think about it. A radio is a device that is used to see. Not hear, because radio is light. To see radio light and convert the light into sound that we can hear. TVs see TV light and convert the light into sound and visible light that we can see. All of it is light. All of this is light. But our eyes can only see small parts of it. So what we use is devices that can see that light and then convert it to light that we can see. That's what night vision goggles do. They take the light that is infrared light and converts it to light that we can see. That's it. All right, but since you were talking about microwaves, and you might be interested, and this is practical, this is how microwave ovens work.
This microwave oven is a truly remarkable feat of engineering. The rapid heating that makes microwaves popular is made possible by power provided from this vacuum tube. Now, if you picture a vacuum tube at all, it's likely in a radio like this. Inevitably, tiny transistors and microchips replace clunky vacuum tubes, but it's too soon to relegate them to the museum. Microchips can't easily replace tubes for producing power, for example, in heating food. Now, a microwave contains three main components. A vacuum tube called a magnetron. It generates the energy that heats food. A waveguide, hidden in the wall to direct that energy to the food, and a chamber to hold the food and safely contain the microwave radiation. In principle, a microwave oven heats no differently than any other type of heat transfer. At a molecular level, heat is a transfer of energy that results in increased motion of the molecules in a substance. Since we aren't quantum-sized, we observe this increase in motion as a rise in temperature. In a traditional oven or stove, we heat food by placing a pan on a burner, or in the oven where the walls radiate heat, which cooks the outside of the food. The insides cook when heat transfers from the surface of the food to its interior. In contrast, energy from the magnetron penetrates into the food, which means the whole mass of the food can be cooked simultaneously. How does it do this? Well, our food is filled with water, which is positively charged at one end and negative at the other. To give these molecules more energy, we expose it to electromagnetic waves that emanate from the tube. By definition, the waves have the electrical and magnetic fields that change.
Okay, so imagine these waves to cause anything that's positive and negative to move around. Water, you know, is polar, has a positive and negative side. So whenever the wave comes around and touches it, it causes it to flip. When it does that, it rubs against the environment, causing friction. So in order for anything to cook in the microwave oven, it needs to be made up of water. That's why pasta, you can stick pasta in there, it's not going to cook.
That's all you have to, or you have to just heat it like 7 times. Put it in spaghetti? No, you have to put it in hot water. Spaghetti.
You have to add water to it. It will not work if there's no water in it.
Like,
If there's
So if I
no
try to
water.
put this in the microwave, it won't work.
Right. It needs to have water. But most foods have water.
Direction rapidly. For this oven, the direction of the fields change 2.45 billion times per second. Water will try to align with the radiation's electric field. The changing field rocks the water molecules back and forth rapidly, and molecular friction from this creates heat as the motion disrupts the hydrogen bonds between neighboring water molecules. Now, you can get an idea of the wavelength of the energy emitted from the magnetron using cheese.
Oh, go back.
Now, you can see on here sections where the cheese.
Okay, so why is it there were sections where the cheese melted, but the other sections where it didn't?
Because it was closer to water.
Because he put it up there and the thing went down. Okay, I don't know.
Okay, remember that the little vacuum tube,
Oh.
okay, releases the microwaves, and the microwaves go through the oven. Only when the microwave, where the microwave intersects with the cheese, can the cheese be heated. So what you're seeing is where the waves came in and out of the cheese.
Cheese is completely melted, and other sections where it's completely unheated. The oven's metal walls only reflect waves of a length that fits inside the oven. This standing wave causes hot and cold spots inside the oven. The three-dimensional pattern of waves is
If we somehow had a device that could allow us to see microwaves, that's what we would see. And only where the cheese comes in contact with the wave will it actually heat up. So guess why you have the little turntable there that turns round and round.
So is that why, like, sometimes, like, there'll be, like, some cold, like, say you, like, heat up some spaghetti, some of it's, like, still cold, and you're like, what? And it's
The
like,
waves didn't hit it. The waves didn't hit it.
I told you, you have to heat it like 7 times.
difficult to predict, but the principle can be seen by looking at the waves in a single dimension. The peaks and valleys in the wave represent the greatest energy of the wave. Well, the nodes here correspond to the cold spots inside the chamber. If I measure the distance between melted cheese spots, I find about 2.5 inches. That would be half the wavelength, the distance between nodes, and is pretty close to the actual wavelength of microwave radiation used. Using that wavelength, I can estimate the microwave radiation's frequency. The frequency is related to the wavelength by the speed of light. I get an answer that only has a 4 or 5% error, not bad for this.
And that's what look at that. Measuring the distance between the cheese where it was melted, he was able to figure out what the number is that's on the box of the microwave. So when you see something like gigahertz, that tells you the waves that are going, that microwave is going to emit. So you can actually predict how far apart the warm and cold areas are going to be in a food. If you did not have the turntable whose job is to try to redistribute the heat.
Primitive measurement. Now, the real engineering in the microwave oven lies in creating the magnetron.
Okay. The rest is really kind of boring physics stuff. How about cell phones? How do they work?
Cell phones. Millions and millions of people use them. With a cell phone, you can talk to anyone on the planet from right where you are. The cellular phone has come a long way in today's society, from the pager, to the first flip phones, to the more advanced, and to the extremely high-tech. Question is, how do cell phones work? It's simple. Cell phones are actually radios. Extremely advanced radios, but a radio nonetheless. The telephone was invented by Alexander Graham Bell in 1876. Wireless communication can trace its roots to the invention of the radio by Nikola Tesla in the 1880s. To understand the sophistication of the cell phone, let's compare it to the walkie-talkie. Walkie-talkies are half-duplex devices. That's when two people communicating use the same frequency, so only one person can talk at a time. A cell phone is a full duplex device. That means you can use one frequency for talking and a second frequency for listening. Both people can talk on the call at once. The genius of the cellular system is the division of the city into small cells. Cells are normally thought of as hexagons on a big hexagonal grid. This allows extensive frequency reuse across the city, so that millions of people can use cell phones simultaneously. So, what happens when someone calls you? When you first power up the phone, it listens for an SID on the control channel. The SID is the System Identification Code, a unique 5-digit number that is assigned to each carrier by the Federal Communications Commission. If the phone cannot find any control channels to listen to, it knows it is out of range and displays a no service message. When it receives the SID, the phone compares it to the SID programmed into the phone. If the SIDs match, the phone knows that the cell is communicating with this part of its home system. Along with the SID, the phone also transmits a registration request. The MTSO, also known as the Mobile Telephone Switching Office, keeps track of your phone's location in a database. The MTSO picks a frequency pair that your phone will use in the cell that will take the call, and once your phone and the tower switch on those frequencies, the call is connected. Now you are talking by a two-way radio with a friend. Cell phone technology has advanced tremendously in the past 20 years. It kind of makes you wonder what the mobile industry has to offer within the many years to come. Digital wireless.
Just a few days ago, I saw this movie with this guy being really cool, carrying one of those big giant phones down. I'm sorry, I'm really old, but I remember sitting there going, "Oh, that is so cool! A phone that you can take with you. That is really neat." So, how do these cell phones work? Well, they are basically a device that helps us to see microwave and radio light. Okay? Not only that, but it also helps us to communicate by sending out microwave and radio light. Now, we do know that certain types of microwaves can adversely affect us by causing our water to spin in place. Could that have a negative effect? Some scientists say yes. Most scientists say no. Some scientists say yes. We are seeing a larger incidence of really weird cancers like brain cancers in Western civilized world countries. Okay, where cell phone use is prevalent. So is it because of our diet? Is it because of cell phones? They don't know for sure. The people who say, yes, this is hurting you, are not saying stop using cell phones. They're saying that we can use them more safely. The safest way to communicate via cell phone is through, you'll love this one, texting. Why? Because it's the antenna that's built into this smartphone that is releasing microwave light and absorbing microwave light. That's the danger. When you energize that antenna and cause it to release the light, that is when you may be the most vulnerable. So as long as you keep it as far away from your body as possible, then you're better off. So if you can't text and you have to call, what's the next thing you should do?
Hold it away. Speaker.
Speakerphone. Use a speakerphone. If you can't use a speakerphone, what's the next thing you should do? The hands-free device. Randy's saying put an aluminum hat over you.
Like the aliens.
Okay, the hands-free device, you know, the earphones with the little speaker and built in. Bluetooth is actually not much better. Why?
It's right next to your head.
Because you're actually inserting a device that is receiving and transmitting radio/microwave light right into your ear. Okay, so no, don't use. People are not using Bluetooth as much as they used to, are they?
I don't know.
Okay, so don't use Bluetooth. Bluetooth is the absolute worst thing you can do is hold it up to your ear. Okay, another thing that you boys should not be doing is something that I catch myself doing oftentimes, especially when I'm at church, because I have Bible apps on my smartphone, so I'm using the Bible app, and you know I'm no longer using the Bible, so I have a tendency to put the cell phone and stick it between my legs. And I start wondering, should I really have something that's transmitting and receiving microwaves that close to sensitive part of me? Okay? And I go, and I usually just take it out, put it in my pocket. Guys, think about that. Your future children are sitting outside of your body. Girls don't have the same problem because their future children are deep inside their body. Okay? Where you're going to have to go through, I know I'm making Ben a little nervous and embarrassed. Okay, Ben, do not put your cell phone between your legs.
I don't think it's funny that you're talking about this.
Well, I'm concerned about some of you procreating, not being able to procreate. But then again, some of you probably don't need to procreate. So, Ben, carry on, son, carry on. Okay, so I'm not worried about procreating. I'm past that. Don't want to procreate. I have nightmares about procreating. Some of you are, all of you guys are at the infant stage of the process of procreating. Hopefully you're at the infant stage, Ben. Okay? So, that's in your near future. For me, it's in my far future, so I don't have as much problem. My far past, please, not my far future. No. Like I said, I have nightmares about the thought of having children. All right, let's see what Hank Green.
So, radioactivity doesn't actually have a lot to do with chemistry in the sense that we've been talking about for most of this course. Chemical reactions happen when an atom's outermost electrons do stuff, and the protons and neutrons and even the inner electron shells are usually completely unaffected. But the protons and neutrons are still part of the atom, of course, still part of the chemicals, and their interactions are important. When protons and neutrons get directly involved in reactions and their numbers do change, huge amounts of energy can be released, far more than by the transfer of electrons that we've learned about in other reactions. When these changes happen to the nucleus of an atom, we rather logically call their study nuclear chemistry. Now, it's probably occurred to you already that changing the nucleus of an atom can completely change its nature. Protons are the key to an atom's identity, so any change that affects the number of protons will turn one element into a completely different one. An alchemist's dream, right? Lead to gold. So as you might expect, that's not something that usually happens in a typical chemical reaction. The same can be said of that other component of the nucleus, neutrons. Atoms of the same element that have the same number of protons, but different numbers of neutrons are isotopes. So changes in the number of neutrons in an atom create different isotopes of the same element. Both of these kinds of changes, changing one element to another or changing one isotope to another, are known as transmutation. And it is indeed possible to transmute lead to gold. It's just so ridiculously expensive that the tiny amounts of gold produced could never pay for the process. But the very fact that it is possible should clue you in that nuclear chemistry is an entirely different flavor of chemistry sauce. Though, as with non-nuclear chemistry, the changes that take place in a nuclear reaction all come down to the atom's desire to have what we all want in life: stability. Just as atoms are most stable when their outermost electron orbitals are full of electrons, certain combinations of protons and neutrons make the nucleus more stable. And just like when an atom gains or loses or shares electrons to stabilize its outer shell, when the numbers of protons and neutrons aren't ideal, the nucleus releases some of them to try to reach a stable configuration. When a nucleus decomposes in this way to form a different nucleus, that's radioactive decay. And
just you undergo radioactive decay. All right, so let's finish this. I can explain the relationship between energy and the frequency and danger to human tissue. I can state which parts of the EM spectrum are ionizing and which are not. Number 6, how are we affected by nuclear radiation is dependent on what? The energy of the radiation. Are you in Myrtle Beach or are you in Panama City? Myrtle Beach is going to have more energy. Panama City, less energy. So who is more dangerous? Myrtle Beach. What is ionizing radiation? It is living in Myrtle Beach, playing in Myrtle Beach, body surfing in Myrtle Beach. One wave after another may just change your atoms into ions. They may knock out electrons from the outermost electrons shell in the atom. And remember, if you change the number of electrons, you change your personality.
Whoa. Look at you.
So, you can change the personality by exposing things to high level energy, ionizing radiation, X-rays, gamma rays, high energy electrons are all ionizing. Ionizing. They can harm us. How can it cause you damage? Like ionization energy, it can knock away electrons from an atom or molecules, changing how it acts. What part of the EM spectrum are ionizing? UV, which we get from the sun. That's what causes you to burn. The nice, pretty, pink color that you get when you have a burn is due to massive cellular damage caused by UV radiation. Many of those cells have died in your skin, and your body's bringing blood toward the surface of your skin in order to break down the dead skin cells and bring in some nutrients in order to try to repair the ones who are not dead. It could be that one of the ones that were damaged has turned into a cancer cell, and that sometime in your near future you will suffer from skin cancer.
Wait, just one cancer cell?
One cancer cell will give you skin cancer. It may take months or years, but it will. X-rays. Of course, you're familiar with that kind of light. It's what's used, will actually go straight through your skin and be absorbed only by your bones and your more dense tissue. Gamma rays is what caused Bruce Banner to turn into the Incredible Hulk. Of course, how is a puzzle to everyone who actually knows about this stuff, because exposing Bruce Banner to gamma rays should have killed him, not turned him into a giant green animal. Cosmic rays is also produced by the sun, and it too was responsible for creating the Fantastic Four. Human Torch, Mr. Fantastic, Sue Storm, and The Thing.
It's called Invisible Woman, not Sue Storm.
Invisible Woman, sorry. Used to be Invisible Girl, but then she became a woman, I guess. All right. Anyway, what should have happened to the Fantastic Four? Should have been the Dead Four. Okay, not the Fantastic Four, the Dead Four. What is non-ionizing radiation? This is lower emissions. The waves are really far apart. It's like Panama City. It's not going to kill you. If you're going to drown in Panama City because somebody knocks you over the head and you become unconscious and you fall into the water, you're not going to drown from being pulled out to sea by a rogue wave or something. We're talking microwaves, radio waves, infrared. And we have all sorts of devices that we can use to see all these types of light, both ionizing and non-ionizing. By the way, if you're ever tempted to go into a room that has this symbol on the door, don't. What does that symbol mean? That means that you have ionizing radiation going around in that room. The more time you spend in that room, the better the chance you get cancer. It always bothered me that the dental hygienist would leave me when she would take an x-ray of my teeth. I would say, no, no, stay. I'm scared. She would go, no, it's against procedure for me to stay. I go, no, but I'm so scared. She goes, no, I have to leave. You know why she leaves? Because she knows that she is hitting you with ionizing light. She knows that she potentially could be causing cancer. She does not want to expose herself to it. That's why she puts the lead apron on you. Because she knows that some of those x-rays scatter and could hit other parts of your body and could hit her. So she leaves the room like the coward that she is. Actually, if you think about it, you're exposed for a brief microsecond. But if she stays in the room and sees 10, 12 patients, she's exposed for a few minutes. So it makes sense that really she needs to leave.
She also has to press a button so it can work.
Yeah, well, the button is designed so that it's somewhere else, right?
Yeah.
So that she has to leave in order and not expose herself. So they'll tell you that it's safe, and it is, relatively.
Okay.
But could one of those bad cells be the one that, could one of those bad rays be the one that gives you cancer? Yeah. The chances are not good, but it's possible. So what is a good analogy to distinguish between non-ionizing and ionizing? Okay, so what if you had a speeding baseball and a speeding bullet, both traveling at the same speed? Which one would you rather be hit by?
Baseball.
Bullet or baseball?
Baseball.
Bullet.
Okay.
Baseball.
Okay, here's the deal. A baseball is going to have a large surface area, right? So when it hits your skin, it's going to do damage. But can it break your skin?
No.
No, because all of that force is going to be distributed over a large area. A bullet traveling at the same speed will be taking all that force and hitting you in a teeny tiny little area. Can your skin withstand that much force? No. So, it could be 6 of one, half dozen, because that baseball is going to do a lot of damage,
It's gonna hurt you.
but it won't go inside of you. The bullet will go inside of you. So the baseball is going to do a lot of superficial damage. The bullet could potentially do a lot of internal damage. And that is the difference between ionizing and non-ionizing radiation. Non-ionizing radiation, if you're being damaged by your cell phone, it's probably very superficially, just like a baseball. If you're being damaged by X-rays or gamma rays or UV rays, it's deep inside of you.
Oh, a baseball? Is it a baseball bat?
No, a baseball.
Well, that would hurt too.
Yeah, I was like, that's
All right.
really bad.